Well, if we look at an equation, a chemical reaction like this, carbon reacting with sulfur to form carbon disulfide. What's being oxidized? What's being reduced? What we've talked about so far doesn't help us with this one. We can't see any ions. This is a molecular compound. There's no ions involved. There's no oxygen, so we can't look at what's gaining oxygen or losing oxygen. We need something else to help us understand what's being oxidized and what's being reduced. That something else is oxidation states. So oxidation states is a concept that helps us to keep track of electrons in chemical reactions. Because what's happening here, there's not an actual transfer of electrons, but electron density is being shifted. And so there is oxidation and reduction occurring here. So it's basically bookkeeping for the electrons, figuring out where do the electrons belong. And what happens is, what we do is we take all of the shared electrons and we assign those to the most electronegative element. So we calculate the oxidation state. It's also sometimes called the oxidation number for each element based on the number of electrons that are assigned to it. Okay, this is not the same as ionic charge. Oxidation state is not the same as ionic charge. What's very confusing is sometimes they are the same number, but they are different concepts. So how do we do this? Well, there's a set of rules. So the oxidation state of an atom in a free element is 0. So anytime you have an element, not an ion, not in a compound, just a single element, the oxidation state is 0. If you have a monatomic ion, like calcium 2+ or chloride 1-, the oxidation state is the same number as the ionic charge. They're different ideas, but the numbers are the same. When we look at a compound, a neutral molecule, all of the oxidation states of the atoms in it have to add up to 0. If you have a polyatomic ion, such as nitrate ion with an overall -1 charge, all the oxidation states of the atoms in it add up to equal the charge. I think this rule is a little bit redundant. Group 1 metals in compounds have an oxidation state of +1. Group 2 metals have an oxidation state of +2. Well, if you look at the ions in these, sodium's always going to be +1 because sodium is always +1 as an ion. And calcium is in group 2, so of course it's going to be +2. The transition metals, though, can form more than one kind of ion, and so they can have different oxidation states. And then the nonmetals have their own little set of rules here. There's reasons behind this, but it's easier to just remember the rules. So this is a hierarchy. I think of it as these nonmetals, we know what ions they would form if they were in an ionic compound. And I think of it as that's the oxidation state that they want to have. But in a covalent compound, there aren't actual charges. And so everybody can't have the oxidation state that they want. And so this is basically a list, and the top of the list, he always gets what he wants. Fluorine in a compound always gets to be -1. After fluorine, hydrogen gets to be +1. That's the charge that hydrogen ion would take as an ion. This is the charge that fluorine would have as a fluoride ion. Oxygen gets to be -2. But sometimes hydrogen beats out oxygen, and oxygen has to be something else. So after those first 3, then it goes group 7, group 6, group 5. So how the heck are you supposed to remember this table? Well, have you heard of Vietnamese noodle soup called pho? It's spelled P-H-O, right? So I'm just going to twist that a little bit. F-H-O. That's close, right? It's the F sound. So F, F-H-O, that's the order here. F-H-O 765. The noble gases get left out of this because they don't make compounds. So fluorine gets his first choice, then hydrogen, then oxygen, then somebody in group 7, group 6, group 5. So those are the rules. Let's practice. Assign an oxidation state to each atom in each substance. So the first one is zinc, Zn. What's the oxidation state? It's 0. Well, the big question is why? Well, it's an element, right? There's no charge indicated, so it's not an ion, and it's not part of a compound. Anytime you just have a single element, the oxidation state is 0. How about Cu2+? 2. The oxidation state is +2. You're not going to get in trouble over this, but I'll just tell you, for oxidation states, we put the sign in front, and for charges, we put the sign after. Just so you know why I'm doing that. So this is +2. The oxidation state is +2 because the charge is 2+. In this compound, how many elements are there? There's 2 elements, so we have to give each of them an oxidation state, calcium and chlorine. This is an ionic compound, right? So what we're going to do is we're going to look at the charges. What are the 2 ions in that compound? Calcium has a 2+ charge, and chlorine has a -1 charge. We know that from their positions on the periodic table. So what's the oxidation state for Ca2+? It's +2. And for chloride? -1. Any questions?
So for oxidation states, you don't add them together to those 2 chlorides, just each one is -1, that's how we answer.
Each one is -1, right? You're looking at the oxidation state for the individual atom in the compound. And notice that this does fulfill that rule that in a neutral molecule or a neutral compound, the oxidation states add up to equal the charge, which is 0. So there's 2 chlorines. They each have an oxidation state of -1, so that's a total of -2. And there's 1 calcium with a +2, and so the oxidation states add up to 0. Let's look at CF4. Is this an ionic compound? No, it's 2 nonmetals, right? If they were going to be ions, we could predict charges off the periodic table perhaps, but they're not ions. So then we have to use that table, or Fa765. Well, we've got carbon and we've got fluorine. Who's got higher priority? Fluorine. What does fluorine want to be? It wants to be -1 because when it becomes an ion, that's what its charge is. So its oxidation state is -1. How do we figure out what the oxidation state on the carbon is?
Fluorine is 4. Is it -1? There's 4 of them, so carbon.
Right. We have to look at the total. The total has to be 0. There are 4 of these fluorine atoms. They each have an oxidation state of -4. -1. They each have an oxidation state of -1. There's 4 of them. So that's a total of -4. And that added to the carbon must be 0. And so the carbon has an oxidation state of +4. Question? Yeah, when you don't just have a simple ionic compound, then you have to add things up together. Okay. Let's look at this one. Now, this is an ion, but it's a polyatomic ion. And so we have to use the rules for the nonmetals to figure out what the charges are on these. So we say Fe765. There's no fluorine, there's no hydrogen, so oxygen gets first choice. What does oxygen want to be? The same as its charge as an ion, -2. Oxygen wants to be -2. So the oxygen has a -2 oxidation state. 765, that would give nitrogen the next priority, but it can't have a -3 oxidation state because the oxidation states of these atoms have to add up to the overall charge. The overall charge is -1. So I'll write this one out. We've got 2 oxygens, and they're each -2, plus that 1 nitrogen, and that has to add up to -1. So this is a total of -4 over here. So what has to go in the blank? 3. Positive or negative? Positive. So the nitrogen here has an oxidation state of +3. Does it have a charge of +3? No. This is nitrite ion. It's the nitrogens and the nitrogen and the oxygens are covalently bonded together, and overall this thing is missing. No, it has 1 extra electron. There's no charges on the nitrogen and the oxygen. But we use the charges that these elements commonly take to help us figure out an oxidation state. Oxidation states are just a made-up thing to help us identify what's being oxidized and reduced. How about SO3? Oxygen gets what it wants because FHO, oxygen gets what it wants, so oxygen gets to be -2. What's the sulfur then?
6.
+6. So the sulfur is +6. We have 3 oxygens. So each of them has an oxidation state of -2. So times 3, that's a total of -6. And all of the oxidation states have to add up to 0 because the charge on this thing is 0. Right? It doesn't have a charge overall. Any questions? So back to this example where we have elemental carbon reacting with elemental sulfur to form carbon disulfide, and we're wanting to know what's being oxidized and what's being reduced. Well, we're going to assign oxidation states. What's the oxidation state of C? It's 0. It's an element. How about S? Just 0. Now, in CS2, who gets priority, sulfur or carbon? Fe765. There's no fluorine, no hydrogen, no oxygen, no group 7. Sulfur's in group 6. So sulfur gets to be what? What it wants. And it wants to be -2 because that's the charge that sulfur takes as an ion. There's 2 sulfurs. They each have oxidation states of -2. That's a total of -4. So the carbon must be +4. This is like some weird game, right? How did I get 4 again? That's a good question. So CS2, overall the charge is 0. So we know that all the oxidation states have to add up to 0. We don't know what the carbon is, but we know that there's 2 sulfurs and they're each -2. So we end up with blank. That's a -4 equals 0. It must be 4. The math isn't hard, you just have to be careful with those negatives. So this gives us another definition of oxidation and reduction. Woohoo! Like we really wanted another one. This one's pretty easy to remember though. Oxidation is an increase in oxidation state, Reduction is a decrease in oxidation state. What's another word for decrease? Reduce. So reduction is a reduction in the oxidation state. So carbon is going from 0 to +4. Is that increasing or decreasing? It's increasing. So the carbon is being oxidized. The sulfur is going from an oxidation state of 0 to -2. Is that increasing or decreasing? Decreasing. Decreasing oxidation state is reduction. So this is being reduced. And that's how you use oxidation states to identify oxidation and reduction when you don't have things with charges. Any questions? So here's a molecular equation, and we're asked to use oxidation states to identify the element that is being oxidized and the element that is being reduced in this redox reaction. Not the compound, the element. So what we have to do is we have to assign oxidation states. I like to start with the elements because they're easy, they're always 0. Which one of these is an element? Tin. So this is 0. And then we've got all these other guys that are messy. Well, the ionic ones, I think, are more straightforward. Of course, some of you might think they're less straightforward, but this is an ionic compound, and it has monatomic ions. It doesn't have any polyatomic ions. Here we've got a polyatomic ion, NO3, so that's a little trickier, but here we just have tin and oxygen. The oxidation states are the same as the charges, the same number. It's not the same concept, but the same number. So what's the charge on oxygen in this ionic compound? What? -2. How do we know that? Oxygen's always -2. You look at the periodic table, you find oxygen, you count backward from the noble gases. 0 for the noble gases, -1 for fluorine, -2 for oxygen. Oxygen forms a -2 ion, always when it forms an ion. So what's the charge on the tin ion in this compound? It's got to be +4. Because the charges have to add up to 0. Okay. So let's do NO2 next. Here we have 2 nonmetals, so we have to do the F thing. FHO. Oxygen gets what it wants. Oxygen wants to be -2. There are 2 oxygens. That's a total of -4 in the oxidation states. All of this has to add up to 0. So the nitrogen must be +4. And here's water. FHO 765. Well, no fluorine, but there's a hydrogen. So hydrogen gets to be what it wants. What does hydrogen want to be? +1. We have to make sure that all those oxidation numbers add up to 0 because this is a neutral molecule. So if there's 2 hydrogens and they're each +1, that's +2. And to get these to add up to 0, the oxygen has to be -2. In water, hydrogen and oxygen both get what they want. In nitrogen dioxide, not so much. The nitrogen doesn't really want to be +4, but oxygen gets first choice, so nitrogen just has to kind of take what's left. Okay, so let's go HNO3. Now we have 3 different nonmetals. Again with the F thing. FHO. Well, there's no fluorine. Hydrogen gets what he wants. +1. Next is oxygen. Oxygen gets what it wants, -2. Now this one you might have to kind of write out to figure out what the nitrogen is. So we've got +1 for the hydrogen and a blank for that nitrogen. And then we've got 3 oxygens, they're each -2. And what does this have to add up to? What's the charge on HNO3? There's no charge, right? Has to add up to 0. So we've got 1 plus something, and this is -6 equals 0. So if we simplify that, we get blank minus 5 equals 0. What's the blank? 5. So the nitrogen over here is plus 5. Any questions? We assigned oxidation states. Now we can identify the element that's being oxidized, the element that's being reduced. The element that is being oxidized will have its oxidation number increase. Well, let's just start at the beginning. Here's tin. Tin goes from 0 to plus 4. That's an increase. So tin is being oxidized. Let's look at hydrogen and see what's happening with hydrogen. Here it's plus 1, and over here it's plus 1. The hydrogen is not being oxidized or reduced. That's okay. We just need to find one thing that's being reduced. So let's look at the nitrogen. It's going from plus 5 to plus 4. That's going down, right? The nitrogen is being reduced. Let's just check the rest of it. What's going on with the oxygen? The oxygen was minus 2. And here it's minus 2, and there it's minus 2, and there it's minus 2. The oxygen wasn't doing anything either. So the tin is oxidized, the nitrogen is reduced. Not the HNO3, the nitrogen in the HNO3. Any questions? That's one that's going to take a while to soak in.